Okay, and now for something completely different, but maybe not completely different. Joao mentioned the overpotential. The overpotential coming from the fact that you have to form interfaces between a gas phase and a liquid. Interfaces, that is a defect ultimately. It's nothing else than an interface that we find also between grain boundaries. We have one grain, some orientation, another grain, same phase, but in between we have an interface. And I want to talk now about how to model grain boundaries in terms of their thermochemistry using constraints. This is work that's based on a transfer approach that we're having in the SFB 1394. That's called, I think, Atomic and Structural Complexity of Defects at Aachen University, together with Ruhr-Universität Bochum, Max-Planck-Institut for Sustainable Materials in Düsseldorf, and the Bundesanstalt für Materialforschung und Prüfung in Berlin. I'm happy to tell you how you can make use of constraints to model microstructure effects. Good, here grain boundaries. This is based on one publication that was kind of the highlight of the first phase of the SFB. The SFB, for those who are not German, this is the largest funding scheme by the German Research Foundation. This was kind of the highlight result of after the first 4 years. The observation that if you have pure gallium, a grain boundary here, a tilt grain boundary, you see these hexagons that are tilted between left and right parts, because this is a tilt boundary. And you see that in between you have these green structure units, which are the grain boundary. And because they used fibbing, using gallium fib actually to produce this TEM sample, they have, with the fib, implanted a bit of gallium into their sample. And what they have observed is that the gallium was partitioning to the grain boundary. So you see the brightness contrast, especially here, for example. You see that there's brighter here, the bright stuff, that is the gallium. And because of the gallium partitioning, also the structure is different. So if you look at the structural motifs here, these red ones, which are the so-called A-type structural motifs, they are different from the T-type structural motifs that you have with the pure magnesium grain boundary. Yeah? And this is the same tilt angle, the same grain boundary left and right. Okay, and then they have developed this defect phase diagram that I don't want to explain in detail here. You can read it up in the publication that's listed down here. Good. When we saw this image, we thought about how to interpret this. Why is there gallium at the grain boundary? What does this really mean? And I want to introduce here a diagram where we have on the x-axis a 10% of gallium, like a typical phase diagram axis. And on the y-axis, I put here something where I say at the bottom we have bulk, at the top we have the grain boundary. Okay, so starting with the first TEM image, we have pure magnesium, HCP, and we have pure magnesium in the grain boundary. As we increase the amount of gallium in the system, we see that we have here something which I would call a three-phase equilibrium, because we have a pure, we have a bulk phase that has a small concentration of gallium in it. But we have here at the grain boundary, we have a part of these green structural motifs, the T-types, and the red ones, the A-type structural motifs, which is actually, I would say, a three-phase equilibrium between the bulk, the A-type, and the T-type. And then as we increase further the gallium concentration going to the right, now we form, we have again a two-phase equilibrium between the bulk here somewhere away from the grain boundary and only the A-type structure unit. Oh, wonderful. Good. This looks to me as a ternary phase diagram, right? This is nothing else but a ternary phase diagram. We have a three-phase equilibrium region, and then we have left of it a two-phase where we have the tie lines, the dashed lines, and right of it we have again tie lines for again a two-phase region. Yeah, and that is wonderful. So the question is, what is this y-axis here that is 0 for the bulk and has some value for the grain boundary. And this y-axis is, ta-da, a constraint. Yes, wonderful. This is a constraint. What does it mean? It means that initially we have nuclei, HTP nuclei, that are forming from the melt, from vapor phase condensation, from whatever. And these nuclei, they have an inclination to each other. They have the same in-plane orientation, the same in-plane orientation, but then no, they have an inclination in plane. Yes, sorry. They have an inclination in plane. They have the same out-of-plane orientation. And that means that if these two grains that are sitting next to each other are growing in size, they must form a grain boundary in between. So the fact that you must form a grain boundary because of the macroscopic orientation of your grains, this is the constraint. So the constraint is the fact that two neighboring grains have a fixed orientation relationship to another. And therefore there must be a grain boundary in between. Okay, now, so we have our constraint axis here, and that means that we can now move, as we move from the lower part to the upper part, that means that we're increasing, we're increasing the number of grain boundaries. That means we're decreasing the grain size. Yeah, and that is just a geometrical conversion, you can believe me. We are forcing more and more atoms to move into the grain boundary by adding more constraint. Good. Wonderful. So this is exactly the amount of atoms that are in the grain boundaries here. And for the related system of a surface bulk system, all of the theory has actually already been published quite a large time ago, or quite a few years ago. There's been work also before that by Tanaka and Perte Kukari and co-workers. And I actually like this formulation by Yunbei Kang here, who has written it up, I think, in a much nicer way than before, describing what's really happening and connecting ultimately the grain boundary, the surface energy in this case, the sigma A, to the Gibbs energy that you have to assign to the end member here. So we have on the x-axis, we have pure A, which is the element A, and here we have pure X, which is the pure constraint. And the surface phase, that is a phase that is here in the middle, combining the physical metal A, or the physical element A, with the unphysical, or the constraint X. Yeah? And it has some stoichiometry. This stoichiometry, that is a bit of magic. How to do this, it's not super trivial, but it can be done, but I don't want to talk about that here. This X is our constraint here, as we used before the QA. This is all the same. Yeah. Good. And then if we see this diagram, this dashed line here, that is a two-phase equilibrium between the bulk and the surface phase, which corresponds also to what we have here in a pure one component system, so one physical component system, pure magnesium, for example. We have a tie line between the bulk magnesium and the surface of the magnesium. Okay, now we have another composition axis here, right? The atomic percent of gallium on the x-axis, and that means that we have to add another axis here into the left-hand side diagram, our Gibbs energy versus composition diagram, which is then the atomic percent of B, let's say. Yeah? And now watch closely as the animation unfolds. Woo! Good. Now we have, I introduced the A to B composition axis here. We still have the AX at the end, at this edge, at the face here in the back. So this dashed line that's here, that is, if we go back, that is exactly the same dashed line as here. I've just moved it in. Okay, good. So, and now we can move into a ternary composition. So we're between the pure A, the pure B, and the X, somewhere here. And then we have a tie line between a bulk phase, which is here at the front, and the surface or the defect phase, which is here at the center. Yeah? and then we can follow how the tie line is oriented to get into this now. Okay, now going back to the grain boundaries, what do we have to do? We have to change this to sigma 7 grain boundary, for example. Actually, that's a sigma 7 with some distinct orientation relationship. And then we replace here A and B, magnesium and by magnesium and gallium. And then, so X is now our concentration of these sigma 7 grain boundaries, which is the inverse of the grain size of the HCP phase. And then this here is maybe our A-type. Yeah? That's the A-type grain boundary. As we've seen before, the magnesium does not only form for this orientation relationship one grain boundary phase, but it forms different grain boundary phases. It can form the A-type, but can also form the T-type. So we have to include another Gibbs energy function here. We have to model this on the grain boundary phase to describe the T-type grain boundary. And then once we have that, we can calculate the ternary equilibrium between the bulk here, the T-type here, and the A-type grain boundary here. Okay, wonderful. How do we do this really in practice? Well, we need data, right? We need to somehow describe the Gibbs energy models of the grain boundaries. And in order to do this, we get data from our partners here in the SFB who calculate using DFT supercells containing such a grain boundary phase. And taking this, we have a formation energy for the end member of our grain boundary phases, both for A-type and for the T-type. And also, we then also ask them to calculate an enthalpy of mixing for a pure magnesium grain boundary, as it includes a bit of gallium here. And it's actually following a nice second order polynomial, so it's a simple regular solution model that we can apply here. We've done this for both, we've done this for the T-type, for the A-type. We actually haven't done it, but we have set up the atomistic simulations to get initial Calphad model for the defect. We have an existing Calphad model for the bulk, and then we have experiments that are stored in a research data management that Aachen University hosted, and we are working on automating all of that route to get into the Calphad optimizer. And once we have it, we can make use of the fact that we know there is a three-phase equilibrium between the A-type, the T-type, and the HCP. We can plug that into the Calphad optimizer in order to exactly reproduce this three-phase equilibrium. And now you see here a defect phase diagram exactly with the gallium on the x-axis, the amount of constraint on the y-axis, where this upper line here corresponds to the composition of the grain boundary phase. And then you can see for the 100 nanometer grain size, that corresponds to this molar amount of X. You just have to trust me on that one. And there exactly we have our three-phase equilibrium. Wonderful. Once we have it, because all of the data is there, we do not only have the three-phase equilibrium data, but we also have data such as the grain boundary energy as a function of composition here on the x-axis again, but also the grain boundary energy as a function of temperature, because we can estimate the also from the atomistic simulations vibration contributions to the defect energy, and then we can calculate here the grain boundary energy in millijoule per square meter for the different grain boundary types. Okay, I will just skip this part. You can do what Philip introduced earlier concerning metastable equilibria. I will just skip this, but because I wanted to quickly show you this one, you can now, if you do this not only for a grain boundary, but also for a twin boundary, you can get a calculation results such as this one, where you see as you enter, so you add gallium to magnesium, and you look at how much gallium is incorporated in the bulk phase, in the grain boundary phase, and in the twin boundary phase. And here you can see the partitioning competition between bulk and microstructural defects. Okay, and you can, of course, also just change the calculation type here to get a partitioning coefficient. Great. Just to summarize, the world is open for Calphad models of grain boundary phases, of defect phases. There's so much work to be done. Yeah, it just took a few decades to get to some decent phase models for steels, for bulk phase models for steels. Now imagine having to calculate or wanting to calculate partitioning at steel grain boundaries and all of the spatial degrees of freedom you have when you orient two FCC or BCC grains with respect to each other, right? You have 4 degrees of freedom. There's a lot to be done there. In order to work on that problem, you need good data formats, and this is something where I just want to do shout out to Flo for his development of the ThermML, which is the XML-based database format that allows to store such information in the future. And yeah, if you're looking for a career perspective in a new field, this one is one recommendation where you can shine and change, I think, how people model partitioning and energies of defects. Thank you very much for the attention.